Today, we're digging into the work of someone who I think truly sparked a sense of wonder for millions, Carl Sagan. People have always looked up at the stars, right? Wondering where we came from, what our place is in this huge cosmos, that search for understanding. It's ancient. But few people have managed to share that journey with such, well, clarity and real enthusiasm as Sagan did.
That's so true. Sagan wasn't just a brilliant scientist, an astronomer. He was this amazing communicator, a kind of bridge, between the sometimes complicated truths of science and just everyday curiosity, our curiosity. There was a review, I think it was the Rhett Lauderdale Sun-Sentinel, that said his work brims with optimism, clarity, and compassion. And that really captures it. He could blend like solid logic and knowledge with actual wit and humor. The Dallas Morning News noted that. Made complex stuff feel, well, enjoyable. He's kind of like that friend who just reads everything and can make even really dense stuff sound fascinating. Inspiring, really.
Definitely. And today we're focusing on one specific book, Billions and Billions, which is especially poignant, isn't it? Described as his most courageous work, a graceful, thoughtful parting gift. It's basically a collection of his final thoughts, published after his death, actually. And in it, he's really grappling with the pressing questions humanity faces, as one paper put it. It feels like his final testament, boiling down his insights right up until the very end, even as he was facing his own mortality.
Yeah, and what's really striking is that, even while dealing with something so personal, his focus was still outward, on humanity's collective future. He wasn't just asking the big questions himself, he was helping us ask them about our planet, our place in the cosmos, the tough choices we face. So our goal here really is to journey through Sagan's thinking in this book. We'll look at quantification, the power of numbers, our spot in the universe, those urgent environmental crises, and some deep moral questions too. We want to distill it down, give you those aha moments so you feel really informed but not, buried in data.
Okay, so to really get a handle on the universe's sheer scale, Sagan starts by making us rethink how we even talk about numbers. And he kicks off with that phrase, the one everyone associates with him, but maybe shouldn't. Billions and billions.
Right. And this is fascinating because despite everyone thinking he said it, all those impressions, Johnny Carson's was famous. Carl Sagan never actually said billions and billions on the Cosmos TV show.
It's amazing how that took off, isn't it? A total pop culture myth. He even said so himself later. I mean, he used the word billion a lot, obviously. How could you not, talking about space? But never that catchy, slightly vague repetition. It just goes to show how ideas spread. But it actually sets up a really important point he makes, how our idea of what constitutes a big number has changed so dramatically.
Exactly. For a huge chunk of history, millions was kind of the top tier. Think about it historically. Earth's population when Jesus lived, maybe 250 million. Casualties in World War I, 40 million. World War II, 60 million. The distance to the sun, 93 million miles. A million was, for a very long time, the go-to large number.
But then things started changing. Our understanding expanded, the scale of things we measured grew, and suddenly billions became, well, almost ordinary. The Earth's age, 4.6 billion years. Global population now pushing past 8 billion, government budgets, hundreds of billions. And I love this detail Sagan includes. He points out that just a few inches is about 1 billion atoms laid side by side, makes this abstract number feel almost physical.
And it doesn't stop there. Sagan notes that even billions is almost becoming passé. Now, trillions is the fashionable big number. Global military spending, almost $1 trillion a year. The U.S. national debt, we're talking tens of trillions now. Distances to stars, like Alpha Centauri at 25 trillion miles. We need these bigger words. It shows how our perception, our frame of reference, has had to stretch just to keep up with what we're discovering.
And because it's easy to get lost in all these zeros, mixing up millions, billions, trillions, scientists came up with exponential notation, which is actually a really neat practical fix. So 1 million is 10 to the power of 6, 1 billion is 10 to the 9, 1 trillion 10 to the 12. It just makes calculations so much simpler and helps us talk about these huge quantities, even if, as Sagan says, nobody can picture 1 billion or 1 quintillion objects in their head.
Right. It lets us handle numbers like, say, the 10 to the 22 stars estimated in the observable universe, or 10 to the 80 elementary particles. Imagine trying to write those out. It would be impossible. And think about counting. Counting to 1 million nonstop would take you over a week. But 1 billion, that's like half your lifetime. And 1 quintillion, 10 to the 18. Forget it. Longer than the age of the universe. It just hammers home the scale we're dealing with when Sagan talks about the cosmos. Clear notation isn't just helpful. It's essential.
And speaking of numbers that make your head spin, Sagan uses this wonderful old story to show the power of growth, especially exponential growth.
Ah, yes, the Persian chessboard story. Or sometimes it's Indian or Chinese, the legend varies. The Grand Vizier invents chess, the king loves it, says, name your reward. The vizier pretends to be humble, asks for just 1 grain of wheat on the first square, 2 on the second, 4 on the third, doubling each time for all 64 squares. The king thinks, wow, modest guy, and agrees immediately.
Big mistake. As Sagan puts it, the king faced an unpleasant surprise. The numbers just explode. They become colossal, staggering. The final total is something like 18.5 quintillion grains of wheat. That's what, 75 billion metric tons? Way more wheat than the whole world produced in a year back then, like 150 years worth. It's such a vivid way to show the insidious power of exponential growth. Starts small, ends unimaginably big.
And it's not just a story, right? This principle is everywhere. Compound interest is a classic example how a small sum can balloon over time. More seriously, he talks about the AIDS epidemic. In its early phase, in many places, it grew exponentially, with cases doubling roughly every year. If that hadn't been slowed down by, natural limits and huge scientific effort, the result would have been an unprecedented catastrophe.
Yeah.
That initial exponential phase, though, still caused immense suffering.
Which brings us straight to one of the biggest challenges we face: world population growth. For most of human history, our numbers were pretty stable. Then came agriculture, and boom, exponential growth started. Right now, the doubling time for the global population is roughly 40 years. If that keeps up, well, you get these unsustainable projections. Malthus warned about this ages ago, population potentially outstripping food supply.
And Sagan is really clear. There's no extraterrestrial solution here. We can't just ship people off to Mars fast enough. Not even close. The only way forward is to slow down our reproduction rate here on Earth. And he points to this key connection, the demographic transition. It's the link between poverty and high birth rates. Basically, exponential population growth tends to level off when extreme poverty disappears. So tackling poverty, providing contraception, empowering women. These aren't just elementary human decency, as he says. They're also acts of self-interest for everyone.
Now, here's a really cool twist on that exponential idea, but looking backward. Our ancestors. Okay, so you have 2 parents, 4 grandparents, 8 great-grandparents. It doubles each generation you go back. If you go back to 64 generations, maybe to around 400 AD, the math suggests you'd have 18.5 quintillion ancestors, which is obviously impossible. That's way more people than I've ever lived.
All right, so what's the catch? The catch is your ancestors weren't all different people. Your family tree isn't a perfectly branching structure. It folds back on itself. We are, as Sagan puts it, repeatedly multiply connected with our relatives. Lots of intermarrying back down the line. This means if you go back far enough, pretty much any 2 people on Earth have a common ancestor. And the takeaway is just beautiful. We are all cousins, everyone on Earth. It's literally baked into our shared history and genes.
So after exploring all these numbers, big and small, growing and shrinking, what's the main point Sagan wants us to take away about quantification? He puts it quite bluntly. If you know a thing only qualitatively, you know it no more than vaguely. If you know it quantitatively, you are beginning to know it deeply.
Numbers aren't just for math class. They're fundamental tools for understanding. Precisely. He gives examples like radioactive dating. That quantitative method gave us a precise date for the Shroud of Turin 14th century, not Jesus' time. It told us when the earliest life appeared about 3.5 billion years ago. The age of the Earth, 4.6 billion years. These numbers move us past just guessing. They give us real deep knowledge. So his conclusion is powerful. Being afraid of quantification is tantamount to disenfranchising yourself. You're basically giving up a key tool for understanding and changing the world. It's about empowerment.
Okay, from the power of numbers, let's shift focus a bit to some very human behaviors. Things that also, maybe surprisingly, link back to our deep past. Sagan paints this picture of Monday night hunters, millions of people watching football or other sports. He says if you analyze it logically, it seems kind of stupid, but at the same time, it's often hard to resist.
Yeah, it's a really interesting observation. We get so invested, right? Cheering for our team. But these aren't skills most of us use daily. Sagan suggests these sports are like symbolic conflicts, thinly disguised. And they have really ancient roots, going back to hunting rituals, even preparing for war. He mentions the Cherokee called their version of lacrosse the little brother of war.
And it's so tribal, isn't it? Teams representing cities or nations. It's us versus them. even when the players are basically mercenaries, switching
Mm.
teams for money. And sometimes that loyalty, that fandom turns really ugly. You get fanatics involved in violence. Sagan argues these strong feelings are hardwired into us, not literally in our brains maybe, but in our genes, inherited from our hunter-gatherer ancestors. That way of life dominated the first, 97% of human history?
And if you look at that hunter-gatherer life, it was nomadic, following game, finding water. There were gender roles. Men often hunted big game. Women gathered essential plants, small animals, maybe even gathered intelligence about neighboring groups or resources. Hunting was this lifelong skill. Boys practiced stalking. Men perfected weapons and teamwork. Emotional control was crucial. Couldn't get too scared or too excited. But importantly, Sagan notes they often had strong social safeguards. Less personal property meant less envy or theft. Things like excessive greed might have been seen as like a mental health issue. Women often held significant political influence. They were largely egalitarian.
So Sagan makes us wonder, are things like Monday Night Football enough of an outlet for these ancient Pleistocene emotions today, especially if we're missing some of those crucial social checks and balances our ancestors had? Even the team names lions, tigers, bears echo those old tribal totems. It really makes you think about how our deep past influences our present, sometimes in ways we don't even realize. How does ancient instinct play out now without those old rules?
From those primal feelings, Sagan shifts again to something just as basic: how we perceive the world, especially through light and sound, across the cosmos. He contrasts the ancient Egyptian pharaoh Akhenaten's idea of light, like the gaze of God coming from the eye, with a much more down-to-earth metaphor: a dripping faucet making waves in a bathtub.
That's such a great, simple image. It helps explain basic wave stuff. Frequency, how often the waves pass a point, wavelength, the distance between the wave crests, and speed, which is just frequency times wavelength. Sound waves, for instance, are these 3D waves moving through the air. Our ears pick them up. And the frequency determines the pitch we hear. Like middle C on a piano, it has a specific, measurable frequency and wavelength, whether you can hear it or not.
And that leads to a really key point about science and reality.
Mm.
What is middle C to someone deaf from birth? Well, it's still 263 waves per second, or hertz. It's a physical property of the world, measurable, objective. It exists outside our personal ability to perceive it. That's fundamental to science-seeking knowledge that goes beyond just subjective experience.
And our ability to communicate language itself is also deeply evolutionary. For hunter-gatherers, speech was vital for survival planning hunts, teaching kids, warning of danger, telling stories. Then came phonetic writing, an astonishing leap, he calls it. Suddenly you could hear someone speaking in our head just by looking at symbols. But spoken language has limits, doesn't travel far, maybe 100 meters. That limitation, plus sparse populations for much of history, likely helped foster isolation, leading to the huge diversity of languages and cultures we see today, all branching from our shared African origins.
Light, though, travels way faster.
Yeah.
186,000 miles per second. And unlike sound, it doesn't need air or anything to travel through it. Crosses the vacuum of space just fine. That's why astronauts can see each other in space but need radios to talk. And this incredible speed creates those noticeable time delays across cosmic distances. You see it in satellite phone calls, a couple of seconds delay talking to the moon, 20 minutes to Mars, even 5 hours for Voyager 2's signal from Neptune. It really grounds you in the vastness.
Light also acts like a wave, creating interference patterns and things like that. But the light we see, visible light, is just this tiny fraction of the whole picture. Different frequencies within that visible range appear as different colors to us. Red is lower frequency, violet is higher. But beyond that, there's this whole electromagnetic spectrum: gamma rays, X-rays, UV, infrared, radio waves. Sagan stresses that each of these is just as legitimate a kind of light as the stuff our eyes detect, and they reveal totally different things about the universe.
Yeah, he calls relying only on visible light chauvinism. We'd miss out on so much, like gamma ray bursts, which are invisible in ordinary light. So why did our eyes evolve to see this specific sliver? Two main reasons, apparently. One, our atmosphere happens to be transparent to visible light, so it actually reaches the ground. Two, our sun pumps out most of its energy in the visible part of the spectrum, and our eyes are most sensitive right around yellow light near the sun's peak output. It's evolutionary pragmatism. The key thing is our senses give us a limited view. Science, using instruments that detect other kinds of light, massively expands what we can perceive.
And even how we see color is interesting. It's mostly about absorption, right? A red rose absorbs most colors but reflects red light back to our eyes. Black and white aren't really colors in the same way. They're about how much light gets reflected. Snow reflects a lot, black velvet very little. And then there's this striking point Sagan makes about skin color and melanin. He says that over most of the spectrum, all humans are black because our organic molecules absorb most UV and infrared light strongly. It's a fascinating scientific perspective that kind of dissolves superficial differences.
And this broader view of the cosmos naturally leads to those big, enduring questions humanity asks. Sagan contrasts ancient creation myth stories trying to explain origins with modern cosmology. Cosmology today isn't just stories, it's based on hard scientific evidence. Evidence for the Big Bang, for an expanding universe filled with maybe 100 billion galaxies, each containing billions of stars like our own drab, humdrum, ordinary sun.
So Sagan laid out what he saw as 4 huge questions where astronomy was poised to make major breakthroughs. He always cautioned, of course, that nature is way more inventive than we are, so the biggest discoveries might be total surprises. But these 4 were ones he found particularly promising.
Okay, first question. Was there ever life on Mars? Mars now looks like a bone-dry, frozen desert. But there's tons of evidence, dried up riverbeds, lake beds, maybe even shorelines suggesting it had liquid water, maybe oceans, about 4 billion years ago, which is right around the time life was getting started here on Earth.
Yeah.
And then you have this Martian meteorites found in Antarctica, like ALH84-1. Inside, scientists found complex organic molecules, PAHs, and tiny structures that look a bit like fossilized bacteria, nanofossils.
But Sagan was always careful, his famous saying, extraordinary claims require extraordinary evidence. And the evidence for Martian life, while really exciting and suggestive, wasn't, in his view, extraordinary enough. Not yet, anyway. So the Mars question holds these 2 huge puzzles. Was there life? And if Mars was once Earth-like, what went wrong? Why the permanent ice age?
Second big question. Is Titan a laboratory for the origin of life? Titan's that big moon of Saturn, right? With the thick, hazy nitrogen-methane atmosphere. Lab experiments that mimic Titan's atmosphere, zapping it with energy, create this reddish-brown gunk. And that gunk contains many of the essential building blocks of life on Earth. Amino acids, components of DNA. Plus, comets hitting Titan over billions of years could have melted surface ice, creating temporary pools or oceans of liquid water. So missions like Cassini, with its Huygens probe that actually landed on Titan back in 2005, were trying to figure out how far Titan has gone on the path to life.
Third question, maybe the most famous one, is there intelligent life elsewhere? The main tool for looking is radio astronomy. Radio waves travel at light speed, go right through gas and dust clouds, and pass through planetary atmospheres easily. Ideal for interstellar messaging. So SETI, the search for extraterrestrial intelligence, uses big radio telescopes to listen for signals that look artificial. They found some tantalizing events, signals that look promising but frustratingly never repeat. So we can't confirm them.
But the search itself is profound, whatever the outcome. If we do find a signal, clearly artificial, wow, our view of the universe and ourselves is changed forever. But even if we search thoroughly and find nothing, that also tells us something important. It helps calibrate the rarity and preciousness of life on Earth. So as Sagan said, either way, this is a search well worth doing.
And the fourth question, the ultimate cosmic question, really. What is the origin and fate of the universe? Sagan felt that modern astrophysics was getting really close to some fundamental insights here. We have strong evidence for the Big Bang, especially the Hubble flow. The fact that galaxies are rushing away from us, and the farther they are, the faster they go, shows the universe is expanding. But will it expand forever, or will gravity eventually pull everything back together in a big crunch?
That depends on how much stuff, matter and energy there actually is in the universe, including all the mysterious dark matter we can't see but know is there from its gravitational effects. These are questions humans have always asked. Is the universe eternal, or did it have a beginning? Will it have an end? But now, crucially, science offers a way to find answers based on real, repeatable, verifiable observations, not just guesses or stories. That's the power of the scientific method applied to the cosmos itself.
Building on that cosmic scale, let's zoom in slightly to planetary systems, including our own, and the sheer number of planets now thought to exist. Remember the Galileo probe plunging into Jupiter back in '95? It confirmed Jupiter's mostly hydrogen and helium with a rocky core. This fits with the old Kant-Laplace idea about how solar systems form, basically. Spinning clouds of gas and dust flatten into disks, and planets condense out of that disk, all orbiting in roughly the same plane. No need for divine intervention.
And we've actually seen this happening. Observations of young stars often show exactly these flat disks of dust and gas around them. Sometimes there are even gaps in the disks, suggesting planets have already swept those areas clean. All this evidence strongly suggests planets aren't rare exceptions. They're probably a common byproduct of star formation, which pushes the estimated number of planets just in our Milky Way galaxy easily, at least into the billions.
And the planets we are finding outside our solar system, exoplanets, are incredibly diverse. It's not all like our neighborhood. First, there was that epical discovery of planets, some Earth-sized, orbiting a pulsar, the dead remnant of a star, totally unexpected. Then astronomers started finding Jupiter-mass planets around normal sun-like stars. They used the Doppler method, looking for the tiny wobble in the star's light caused by the planet's gravity tugging on it.
But the really surprising thing was where some of these giant planets were. Many of them, like the one around 51 Pegasi, were very close to their stars, orbiting much faster and closer than Mercury orbits our sun. That really threw a wrench into the standard theories, because we thought gas giants like Jupiter could only form out in the cold outer parts of a solar system disk. How did they get so close in? Maybe they formed far out and migrated inwards. It's still debated. Other techniques, like astrometry precisely measuring a star's position, hinted at maybe more familiar systems, like possible Earth-like planets around Lalande 2185. The big takeaway here is that planetary systems seem to be common, but they come in a wild variety of configurations. Our solar system might not be the norm at all.
And the search continues. Newer methods, interferometers, adaptive optics, looking for gravitational lensing, or tiny dips in starlight as planets pass in front, are expected to find hundreds of other planetary systems, including, hopefully, a few small blue worlds graced with water oceans, oxygen atmospheres, and the telltale signs of wondrous life.
Which makes our own small blue world seem even more special, doesn't it? Sagan illustrated this beautifully with a personal story about a little sealed glass sphere he had, a crystal world. Inside were just some tiny shrimp and algae and water, a completely closed ecosystem. The shrimp ate the algae used the shrimp waste and sunlight, they breathe each other's waste gases, recycle everything, an extremely intimate relationship.
But Sagan describes how he got really attached to these little shrimp, worried about them, and felt genuine grief when they eventually died out. He realized this feeling stemmed from a fear of a parallelism between their world and ours. Because Earth, too, is a larger but still fundamentally closed ecosystem. Humans, plants, microbes, we all live off each other, breathe and eat each other's waste, depend on one another.
And we humans are relative newcomers. Our species is maybe a few million years old, but our technological civilization, just a few hundred. We don't have a long track record of interspecies or even interspecies cooperation, as Sagan dryly puts it. We're often focused on the short term. But the planet itself operates on interconnected global cycles. Oxygen from the Amazon rainforest benefits North America. Acid rain from U.S. smokestacks damages Canadian lakes. Chernobyl radiation shows up in reindeer in Lapland. Chinese coal burning affects temperatures in Argentina. CFCs released anywhere thin the ozone layer protecting New Zealanders. Diseases spread globally. The point is inescapable. Earth is one system. Our actions have global consequences.
And our technology has reached, well, astonishing proportions. But Sagan worried that we are inadequately prepared, mentally or emotionally, for the power we wield. He imagined how utterly mind-blowing things we take for granted, like jet contrails or spacecraft, would seem to hunter-gatherers, or even his own grandparents, like awesome wonders from the future. It highlights this huge gap between our technological capability and our collective wisdom to manage it.
Which creates this real dilemma for scientists, doesn't it? The tension between sounding the alarm and offering reassurance. Many scientists see real dangers ahead, warning that our industrial civilization could be a kind of booby trap. But people resist these warnings for lots of reasons. It's expensive to change, it hurts profits, it makes us anxious. Sometimes there are Pollyannas saying, nothing to worry about.
And here's the paradox, Sagan points out. Scientists are trained to be skeptical, right? To demand strong evidence for extraordinary claims like UFOs or psychic powers. So how can they turn around and say that other extraordinary claims like potential environmental catastrophes must be taken seriously and considered urgent?
Sagan's answer is direct. Because our lives depend on minuscule amounts of such gases as ozone, for example. And because our ability to fundamentally alter the global environment is now beyond question. It's not speculation anymore, it's observed reality. He wondered if humanity has grown up enough for the power we have, comparing it to giving a handgun as a present to an infant.
It's hard to think clearly when the stakes seem so high. People tend to swing between denial, it's not happening, or panic, we're doomed. Sagan's goal in writing about these difficult topics was to provoke contemplation, to encourage us to think about long-term consequences, to use that capacity for foresight that's been part of our proud lineage among us primates, and to engage with the scientific evidence soberly without giving in to wishful thinking or despair. The key takeaway is that responsible skepticism means paying attention to well-founded warnings, especially when the evidence is strong, even if the message is alarming. Right, as we delve into these big challenges, Sagan uses two ancient figures, Croesus and Cassandra, to illustrate how we often react or fail to react to warnings. Remember Croesus, the super-rich king? He asks the oracle at Delphi if he should attack Persia. The oracle says he will destroy a mighty empire. Croesus, blinded by wishful thinking and greed, assumes it means he'll destroy Persia. Nope. He destroys his own empire, Lydia.
Yeah, a classic case of hearing what you want to hear. Credulous acceptance because it fits your desires. Then you have Cassandra, the Trojan princess. Apollo gives her the gift of prophecy, but because she spurned him, he adds a curse. No one will ever believe her. So she foresees everything, the Trojan horse, Agamemnon's murder, her own death, but nobody pays attention. She's just written off as a prophet of doom and gloom.
So Croesus and Cassandra's listeners represent these two extremes of policy response. Gullible belief on one side and stolid, immobile rejection of unwelcome truth is on the other. The challenge for policymakers, and for all of us really, is to find that prudent course in between.
And science, Sagan argues, gives us tools for doing that. It has built-in error-correcting procedures. Things like arguments from authority don't count for much. You need evidence. Quantitative predictions are better than vague ones. Ideas need to be consistent with other known facts. Vigorous debate is actually healthy. And crucially, findings need independent confirmation by different groups. But using these tools effectively requires, as he says, emotional discipline and a scientifically literate citizenry. People like you, basically, who can weigh the evidence for yourselves. The aha moment is that navigating danger isn't about gut feelings or blind trust. It's about applying these rigorous evidence-based methods.
And speaking of warnings ignored and then confirmed, let's talk about a piece of the sky is missing, the ozone layer crisis. This is such a perfect example of the Croesus-Cassandra dynamic. We all know ozone down here near the ground is bad, right? Smog, pollution from cars and industry. But way up high, 25 kilometers or so, ozone O3, 3 oxygen atoms forms naturally when UV sunlight hits regular oxygen O2. And that high-altitude ozone layer is vital.
Then, back in the 1920s, chemists invented these chemicals called chlorofluorocarbons, CFCs. And they seemed amazing. Non-poisonous, non-flammable, super stable, perfect for refrigerators, air conditioners, aerosol pans, wildly successful. For decades, we used billions of tons of them, and no harm seemed ever to come from it.
But there was a hidden danger, an invisible threat. Because they were so stable, CFCs didn't break down near the ground. They slowly drifted up over years into the stratosphere. Up there, the intense UV sunlight can break them apart, and when that happens, they release chlorine atoms. And here's the scary part. A single chlorine atom acts as a catalyst. It can zip around destroying ozone molecules one after another, taking out maybe 100,000 ozone molecules before it finally gets washed out of the atmosphere.
And why is losing some invisible molecules way up there such a big deal? Because that ozone layer, even though it's incredibly thin, if you brought it all down to sea level pressure, it'd only be 3 millimeters thick. That thin layer is all that stands between us and the fierce and searing long-wave UV from the sun. Without it, or if it gets significantly thinner, we see big increases in skin cancer, especially for light-skinned people, eye cataracts, damage to immune systems. But the really terrifying potential impact, Sagan notes, was on phytoplankton, the tiny plants at the base of the entire ocean food chain. Killing them off could cause ecosystem collapse, mess with CO2 absorption, even damage land crops. Even just a 10% global reduction in ozone looks to be very dangerous.
The story of how this was figured out and the resistance it faced is telling. Rowland and Molina first published their warning in 1974. They eventually won a Nobel Prize for it. But DuPont, the main manufacturer of CFCs, making hundreds of millions a year from them, fought back hard. They ran ads, lobbied Congress, called the science unproved, exaggerated, based on faulty scientific reasoning. They warned about businesses destroyed by premature legislated action. Sound familiar?
Yeah. And for a while, it worked. Public concern faded a bit, but all the while, CFC levels in the atmosphere kept climbing. Chlorine levels got way higher than they'd been naturally. Then, the bombshell in 1985. The discovery of the Antarctic ozone hole, a massive, nearly 50% depletion of ozone over the South Pole each spring. No scientist had predicted it.
Yeah.
Even then, some industry groups tried to downplay it, but the evidence linking CFCs to the hole soon became irrefutable. The good news is the world actually listened eventually. The Montreal Protocol was signed in 1987, phasing out CFC production globally. It takes a long time for the CFCs already up there to dissipate, like a century, but measurements show chlorine levels are finally starting to decrease.
It's such a crucial lesson, isn't it? The ozone story is a template for many other environmental threats. It shows how seemingly harmless industrial actions can have unforeseen global consequences that need long-term international solutions. It also shows that global action is possible, even against powerful vested interests, when the scientific evidence becomes undeniable. It's a story of both peril and, ultimately, successful global response.
And that leads us right into another major global threat, also linked to industrial activity and our energy use. Global warming, driven by our addiction to oil and other fossil fuels. That addiction doesn't just cause environmental problems. It fuels wars, creates economic instability, and pumps enormous amounts of carbon dioxide, CO2, into the atmosphere. And CO2 is a greenhouse gas.
Right, the greenhouse effect.
Yeah.
We need to understand this. If Earth had no atmosphere, basic physics says its average temperature would be about 20 degrees Celsius below freezing. Pretty cold. But we have an atmosphere, and certain gases in it, mostly water vapor, CO2, methane, even those CFCs act like a blanket. They let visible sunlight in, but they trap some of the infrared heat that Earth radiates back out. That trapping warms the planet by about, 33 degrees Celsius overall?
Exactly. So a little greenhouse effect is a good thing. It makes Earth habitable. The problem is when we add more greenhouse gases, like CO2 from burning fossil fuels, that thickens the blanket, traps more heat, and warms the planet further.
And if you want a really dramatic, practical demonstration of this, Sagan says just look at Venus. Its atmosphere is incredibly thick, almost 90 times Earth's pressure, and it's mostly CO2, the result. A surface temperature hot enough to melt lead 470 degrees Celsius. That's a runaway greenhouse effect. A cautionary tale, perhaps, for anyone claiming the whole thing is a hoax.
And the human impact on CO2 levels isn't really debatable. We dump about 7 billion tons of carbon into the atmosphere each year from burning fossil fuels and deforestation. That's way more than natural systems like oceans and forests can absorb quickly. The proof is in the measurements, like the famous Keeling curve from Mauna Loa in Hawaii. It shows CO2 concentration steadily rising year after year, even in a location far from major industry. It's a global phenomenon. And climate models, which try to predict the effects, have consistently shown that this increase should cause warming. The observed warming trend over the 20th century fits these predictions.
We're seeing the signs now, aren't we? Arctic sea ice shrinking, glaciers retreating worldwide, and Arctic ice shelves collapsing, more extreme weather events, sea levels slowly rising. The scientific consensus is overwhelming. The Intergovernmental Panel on Climate Change, the IPCC, concluded back in 1995 that there was a discernible human influence on climate. The certainty has only grown since then.
Now, the climate system is incredibly complex. There are feedback loops. Some are positive, meaning they amplify warming, like melting ice, reducing reflectivity, causing more warming. Others are negative, potentially counteracting warming, like more clouds reflecting sunlight, or faster plant growth absorbing more CO2. Predicting the exact outcome when you balance all these feedbacks is tough. Nobody is absolutely sure about the precise magnitude or speed. But the models, calibrated against past climate data, seem to be broadly accurate. The basic physics is solid.
But finding solutions runs into huge political and economic hurdles. The U.S. has historically been the biggest emitter, but China's catching up fast. Developing countries are also increasing emissions. So any real solution has to be global. But politicians everywhere tend to focus on short-term election cycles, not the 20 to 60-year timescales needed for effective climate action. Sagan draws an analogy to engineering. When you build a bridge, you build in huge safety margins because the consequences of failure are catastrophic. Why don't we apply the same caution to protecting the global environment?
He points to key areas for action. Fuel efficiency is a big one. He criticized the auto industry for resisting higher standards, arguing safety could be improved without making cars huge, and that Americans do care about the environment. Alternative energy is crucial. He acknowledged the issues with nuclear fission waste, accidents, public perception. Fusion power is still decades away if it ever works commercially. Relying on some unforeseen breakthrough is foolhardy. The real promise lies in renewables. Solar, wind, geothermal. He pointed out that even back then, wind was becoming cost competitive with coal if you included environmental costs, and solar photovoltaic costs were dropping rapidly.
And he argued that if you factor in the true costs of fossil fuel subsidies, military spending to protect oil supplies, health impacts, environmental damage, then renewables like solar and wind were already much cheaper. The U.S. had, and maybe still has, an opportunity to lead the world in developing and deploying these technologies.
And then there's reforestation. Planting trees is the only method of cooling down the greenhouse effect, which seems both safe and reliable. But it requires a massive global effort, reversing current trends of deforestation.
The bottom line for Sagan was that despite the immense challenge, we know what to do. He saw a potential silver lining. These global environmental crises force us into a new kind of thinking. They compel us to prioritize the well-being of the human species over narrow short-term interests. They could actually lead to a binding up of the nations and the generations. It's a call for foresight, cooperation, and recognizing our shared fate on this planet.
From these planetary threats, Sagan then shifts to our internal divisions, our tribalism. How do we overcome those? He mentions Ronald Reagan's offhand remark that maybe an alien invasion would finally unite humanity. Sagan's response was sharp. We don't need aliens. We already have common enemies. The unprecedented menace comes from our own technology, our own short-sightedness, our own divisions.
Yeah, he lists the examples again. CO2 warming affects everyone's bread baskets. CFCs deplete ozone globally. Acid rain crosses borders. Chernobyl's fallout spread far and wide. Epidemics don't respect passports. And looming over everything during the Cold War, those 60,000 nuclear weapons. A global booby trap set by the US and the Soviet Union. Each side built up its arsenal, justifying it by pointing to the other, locked in this deadly embrace.
And he does this really interesting exercise. He asks you to try and see history from the other side. So he outlines U.S. history from a critical Soviet perspective, mentioning things like slavery, broken treaties with Native Americans, the use of the atomic bomb, interventions in other countries. Then he flips it, outlining Soviet history from a critical Western perspective, military expansionism, Stalin's atrocities, the invasion of Afghanistan, lack of civil liberties. His point isn't to say one side was right and one was wrong. It's to show how easy it is to demonize the other side by focusing only on their flaws while ignoring your own.
This habitual enmity, he calls it, becomes self-perpetuating. Old grievances, stereotypes, caricatures of communism or capitalism just keep the divisions alive. He argues forcefully that no nation is yet well fitted to the world of the 21st century. Glorifying your own past or defending every national icon uncritically is dangerous.
He holds up science as a better model. To understand complex issues, we must try to free our minds of dogma and to guarantee the freedom to publish, to contradict, and to experiment. Unquestioning loyalty, like the Nazi official Rudolf Hess saying Hitler was beyond all criticism, is, Sagan says, suicidal for nations.
So what's the way forward? Reduce military spending, that $1 trillion a year globally, is a scandalous waste. Invest in raising living standards, education, science, free inquiry. Acknowledge our common humanity and our common jeopardy.
And this requires, again, those expanding horizons of identification, moving beyond loyalty just to your family or tribe or nation state. He believed the next necessary step is identifying primarily with the planet Earth and the human species. The urgent, critical question is whether the fundamental unit of identification will expand or whether we will destroy ourselves first. He feared it's going to be very close. Cooperation on arms, the economy, the environment isn't optional anymore. We must all help one another or all perish together. That's the stark choice. It's a powerful aha moment about our interconnectedness.
Now, shifting gears to a deeply divisive social issue, Sagan, writing with his wife Andrian, took on the complexities of abortion. They start by acknowledging the intense polarization, the accusations of hypocrisy and murder, how it divides families and becomes political football. You have the two main absolutist camps. Pro-choice, arguing it's solely the woman's decision, and pro-life, arguing life begins at conception and abortion is murder.
But Sagan and Andrian then systematically challenge the certainties of both sides. For the pro-choice absolute, if a woman has total control over her body, what about a late-term fetus, moments before birth, which is essentially identical to a newborn child? Is it okay to kill it then? If not in the 9th month, what about the 8th? Or the 7th? Where do you draw the line? That's the slippery slope argument they raise. They also note the suspicion that some abortion bans are less about fetal life and more about controlling women, forcing unwanted pregnancies on the poor, teenagers, or victims of rape or incest.
Then they turn to the pro-life absolute. If life begins at conception and any termination is murder, they counter that life does not begin at conception. It is an unbroken chain going back billions of years. Sperm are alive, eggs are alive. Is destroying them murder?
What about masturbation, releasing hundreds of millions of sperm? Is that mass murder? What about cloning? If any body cell could potentially become a human, is shedding skin cells mass murder? These questions expose the difficulty of defining the start of human life in purely biological terms.
They also point out the inconsistency of some pro-life stances that allow exceptions for rape or incest. If the fetus has an absolute right to life, why should the circumstances of conception matter?
And why do many abortion opponents also oppose contraception and sex education, which are proven ways to reduce the number of abortions?
They delve into the history, too. The idea of ensoulment, when the soul enters the body, has been debated for centuries, even by major theologians like Augustine and Aquinas, who didn't consider early abortion homicide. Later, church views hardened, partly influenced by early microscope observations that mistakenly seem to show tiny, fully formed humans, homunculi, in sperm.
Even the American Medical Association's push for anti-abortion laws in the 19th century was partly motivated by professional power struggles, not just purely scientific or moral conviction.
So if biological life isn't a clear starting point for absolute protection, what is? Sagan and Druin argue the key question is, when does personhood emerge? We consider killing a human murder but not killing a chimpanzee, though maybe we should think harder about that.
No.
The difference lies in personhood.
Acknowledging that drawing a line is inherently difficult, they argue for drawing it conservatively, meaning early, but based on relevant criteria. What makes us uniquely human?
They review fetal development. At 4 weeks, it resembles a newt or tadpole. At 6 weeks, a reptilian face. At 8 weeks, a primate-like face with basic reflexes. But reflexes, motion, breathing, these aren't uniquely human. Animals do them. What is uniquely human, our one great advantage, is characteristically human thought, centered in the cerebral cortex. So their proposed criterion is pragmatic. Draw the line when the beginning of characteristically human thinking becomes barely possible.
Based on brain development and the emergence of coherent brainwave patterns, this seems to happen much later in gestation, certainly not at conception, probably not even in the first trimester, maybe closer to the start of the third trimester, around 6 months.
This timeframe aligns roughly with the framework established by the U.S. Supreme Court decision Roe v. Wade.
Roe v. Wade itself focused on balancing the woman's right to privacy against the state's interest in protecting potential life. It allowed states to restrict abortion more as the pregnancy progressed, particularly after viability, the point where the fetus could potentially survive outside the womb. But Sagan and Druin critique viability as a standard. It changes with medical technology incubators, future artificial wombs. Does morality depend on technology? That seems fragile. A newborn isn't viable without care either. So they conclude viability isn't a coherent basis for determining when abortion is permissible. They return to their criterion, the earliest onset of human-like thought patterns. On that basis, they viewed Roe v. Wade with its trimester framework allowing early abortions but restricting late-term ones as a good and prudent decision that struck a fair balance in a complex issue with no easy answers.
Okay, from those really tough ethical questions, let's look at the rules of the game, how humans interact, cooperate, or compete. Ethics and strategy. Sagan notes that moral codes exist in all societies, from ancient Babylon to hunter-gatherers. They vary, but often have a pragmatic core.
Yeah, there's this tension. If, even in the long run, ethical behavior were self-defeating, eventually we would not call it ethical, but foolish. So what works?
He reviews some common rules. The golden rule. Do unto others as you would have them do unto you. Sounds great, but has limits. What if the other person is a masochist or utterly ruthless?
Then there's the silver rule. Do not do unto others what you would not have them do unto you. Maybe more practical. Gandhi and Martin Luther King Jr. powerfully used versions of these through nonviolent resistance. Though, Sagan notes, the threat of violence by others might have also played a role in their success.
The brazen or brass rule. Do unto others as they do unto you. Basically reciprocity, an eye for an eye, but also one good turn deserves another. Very common in human and even chimpanzee societies.
And then the less admirable ones, the iron rule. Do unto others as you like before they do it unto you. Might makes right. The tin rule. Suck up to those above you and abuse those below. And the nepotism rule. Favor your relatives above all else.
To explore which strategies work best, especially in situations where interests conflict, Sagan turns to game theory, specifically the prisoner's dilemma. We often default to zero-sum thinking, for me to win, you have to lose. That comes from our tribal past.
But many modern problems are lose-lose, nuclear war, climate change, economic collapse, or potential win-win friendship, love, scientific discovery. The prisoner's dilemma set up two suspects interrogated separately. Deciding whether to betray the other or stay silent shows how individually rational choices, betraying, can lead to a worse outcome for both than if they'd cooperated, stayed silent.
But what happens if you play the game repeatedly? Experience matters, strategies evolve.
And computer tournaments running thousands of simulations found a remarkably simple and effective strategy consistently won. Tit for tat. How it works. Start by cooperating. Then in every following round, just do whatever your opponent did to you last time. It's nice, starts cooperatively. Retaliatory, punishes defection immediately. Forgiving, returns to cooperation if the opponent does. And clear, easy to understand. It's basically the brazen rule, but with an optimistic first move.
What's fascinating is that tit for tat reflects reciprocal altruism, a behavior seen widely in the animal kingdom, suggesting deep evolutionary roots for these cooperative competitive strategies.
The key insight from this game theory exploration is that while real life is more complex, strategies based on reciprocity, starting with cooperation but responding promptly to both cooperation and defection, tend to be highly successful in fostering long-term beneficial interactions. Forgiveness also turns out to be surprisingly powerful.
Now, let's connect those rules back to a stark historical reality with Gettysburg and now. Sagan uses the Battle of Gettysburg as a grim milestone. 51,000 casualties in 3 days. It represented the dawn of truly industrialized warfare, mass-produced weapons, railroads for transport, early machine guns, like the Spencer repeating rifle, even aerial reconnaissance from balloons.
And from that point, the destructive power of weapons escalated exponentially. It's terrifying when you lay it out. A cannon at Gettysburg, maybe 20 pounds of TNT equivalent, kills a few people. A WWII blockbuster bomb, 10 tons of TNT, 1,000 times bigger, kills dozens, maybe hundreds. The first atomic bomb, 10,000 tons of TNT equivalent, another 1,000-fold jump, kills hundreds of thousands. Then the hydrogen bomb, 10 million tons of TNT, another 1,000 times more powerful than the atomic bomb. The bottom line is chilling. In barely a century, our most fearful weapon has become 1 billion times more deadly. But, Sagan asks, have we become 1 billion times wiser? The answer seems obvious.
We created that nuclear booby trap, nearly 60,000 weapons at the peak of the Cold War, enough to destroy global civilization many times over. No nation, no man should have such power.
He called the arms race a fool's bargain. After WWII, the US and Soviet Union felt invulnerable to conventional attack across oceans. But by building vast nuclear arsenals aimed at each other, they made themselves exquisitely vulnerable to instant annihilation, his words. If Moscow decides we should die, 20 minutes later we're dead, and vice versa.
We literally bet our survival on the perpetual sanity and sobriety of leaders in multiple countries forever. That, he argued, is asking too much of us. Because we make mistakes, we kill our own. He cites Challenger, Chernobyl, Hitler, Stalin as examples of catastrophic errors and failings.
The cost wasn't just the risk of annihilation. It was trillions of dollars spent, $10 trillion by the U.S. alone during the Cold War, diverted from healthcare, education, infrastructure. Plus the immense psychological burden of living under that nuclear sword of Damocles.
And even after the Cold War, global military spending remained incredibly high, close to $1 trillion a year, mostly on conventional weapons, with the U.S. and Russia as leading arms dealers. A scandalous waste.
But the end of the Cold War also presented an opportunity. Reductions in conventional forces, redirecting military funds to human needs. He called for recognizing freedom fighters in other costumes, supporting nonviolent change, expanding our definition of liberty beyond just our own liberty.
It comes back to that theme of union and expanding identity. Just as the U.S. Civil War was fought brutally to preserve the Union and expand the concept of who belonged, Sagan argued the next necessary step is global.
If we do not destroy ourselves first, the unit of primary identification will before long be the planet Earth and the human species. It's not idealism, it's practical necessity. Nations now can only rise and fall together.
Yet even when Billions and Billions was published in the mid-90s, he noted the resistance. Treaties like the Chemical Weapons Convention, signed but not ratified by key players like the U.S. and Russia. START II nuclear reductions stalled.
He criticized the massive U.S. military budget, still at Cold War levels, questioning why it was sacrosanct, while social programs faced cuts. Spending billions on things like space-based missile defense against non-existent threats seemed ludicrous when real problems like nuclear waste cleanup, costing hundreds of billions, were being left to future generations.
His question resonates today. Why do we have such difficulty grasping that national security is a much deeper and more subtle matter than the number of rocks in our pile?
Finally, Sagan reflects on the 20th century as a whole, a time of almost unbelievable transformation, both wondrous and terrifying. Communication technologies, radio, TV, eventually the internet shrank the globe, enabling mass entertainment but also facilitating political change, like Tiananmen Square or the fall of the Berlin Wall.
Yet he also saw signs of decline. Particularly in the U.S. at the time, high infant mortality compared to other developed nations, disproportionate incarceration rates, lagging science education, widening inequality. He linked this partly to a dwindling penchant for critical thinking and political action.
And the century's technology enabled killing on an unimaginable scale. From WWI artillery barrages to nuclear weapons, chemical and biological agents. Over 150 million people killed by war or dictatorial decree in that century alone. Genocide became industrialized. Technology made mass killing practical, often creating a distance that numbed conscience. And that trillion-dollar annual global military budget persisted, a scandalous waste diverting resources from real human needs.
But alongside the darkness, there were the incredible revelations of science. Physics gave us relativity and quantum mechanics, unlocking the atom, fission, fusion. Radioactive dating finally gave us firm ages for the Earth, 4.6 billion years, and the origin of life, around 4 billion years ago.
Biology was transformed by the discovery of DNA, cracking the genetic code, mapping the human genome. Life became understandable in terms of chemistry and physics. No life force, no spirit, no soul seems to be involved. Molecular biology revealed our incredibly close kinship with chimpanzees, 99.6% shared active genes. Field studies showed chimps capable of compassion, planning, tool use, even basic politics.
The origin of life itself started to seem less mysterious, with experiments showing how building blocks like amino acids could form naturally under early Earth conditions. Much of biology, Sagan wrote, is reducible to chemistry, and much of chemistry is reducible to physics, a profound unification of knowledge.
And astronomy exploded. We found planets around other stars, grasped the scale of our Milky Way, 400 billion suns, and the universe, 100 billion other galaxies, traced cosmic history back to the Big Bang, discovered bizarre objects like pulsars, quasars, black holes. Science put us on the verge of answering the deepest questions humans have ever asked.
Which brings us, finally, to Sagan's most personal reflections in the book, In the Valley of the Shadow. He writes with raw honesty about facing death multiple times from myelodysplasia, that rare blood disease. 6 times, he says, he came close. Through this ordeal, he learned so much about the beauty and sweet poignancy of life, about the preciousness of friends and family, and about the transforming power of love.
He admits he wished for an afterlife, for a reunion with lost loved ones. But based on the evidence, he knew of nothing to suggest that it is more than wishful thinking. And that very lack of certainty, he says, gave him a little extra motivation to stay alive, to cherish the one life he was sure of.
He recounts the medical journey. The diagnosis, maybe 6 months to live. The desperate search for a bone marrow donor. His sister Carreri was a match. The treatment at the Fred Hutchinson Cancer Research Center in Seattle.
He describes the brutal chemotherapy, taking pills marked biohazard, feeling like he was swallowing a fatal dose of arsenic. Then the transplant itself, surprisingly simple, just like a blood transfusion.
His body became a chimera, his blood and immune system derived from his sister's female XX cells, while the rest of his body remained XY male. He jokes it didn't change his interests, no sudden urge to take up knitting instead of horse riding.
He emphasizes the critical role of support, his wife Annie, as his designated caregiver, the presence of loved ones being vital for survival.
And he expresses profound gratitude for the medical research, both basic and applied, that made the treatment possible, for having medical insurance, acknowledging the privilege many lack, even for the animal research, despite his ethical conflicts, stating bluntly, "I would not be alive today if not for research on animals."
He experienced remission, a brief return to work and life, proofing the book, visiting the set of the Contact movie. But the disease returned. More treatments. Through it all, he found inspiration in the community of goodness, the millions who donate marrow or blood, the dedicated scientists and healthcare workers. It showed him how pervasive goodness is.
People of all faiths prayed for him worldwide. Though skeptical about prayer influencing outcomes, he felt deep gratitude for their compassion.
He directly addresses the question people often asked: how is it possible to face death without the certainty of an afterlife? He shares his perspective, echoing Einstein, finding fulfillment in understanding the marvelous structure of the existing world, grasping even a small part of the reason that manifests itself in nature, and cherishing the connections we have in this life.
After a final relapse facing pneumonia, he describes a sense of calm acceptance. "This is a death watch," he told Annie. His final words were to his young son. Annie recounts letting him go without fear.
His legacy endures: his children, his books, and those Voyager spacecraft carrying messages of a tiny world graced by music and love, continuing their journey toward the stars and a destiny about which we can only dream. Facing death became For Sagan, not a reason for despair, but a profound catalyst for appreciating life, love, and the power of human knowledge and kindness.
So as we wrap up this deep dive into Carl Sagan's final reflections and billions, it really feels like we've covered vast territory, from, the mind-bending scale of cosmic numbers and our place within that, to the very real, very urgent environmental crises on our own planet and those deep human moral questions, all seen through Sagan's unique lens, that mix of absolutely scientific rigor and this deep, compassionate humanism.
Absolutely. And that core message echoes throughout. We need critical thinking. We need global cooperation. We need to expand our identification horizon beyond narrow tribalism if our species is going to make it, let alone thrive. He wasn't just saying these things are nice ideas. He argued they're practical necessities now. These global problems, environmental, military, social currents, they force us into a new kind of thinking, where the long-term well-being of everyone has to come first.
And hopefully by exploring these ideas with us, you, listening right now, feel better equipped, not necessarily with all the answers, but with the understanding to engage thoughtfully with these pressing questions humanity faces. It's about having the context, the background, so you're not just overwhelmed by the headlines, but can actually think critically about the challenges and the potential solutions.
Exactly. So maybe the thought to leave you with is this. If Sagan is right, if the universe truly is this vast, interconnected, astonishing place, and if we, and tiny as we are literally made of star stuff and have evolved this capacity to understand it, even a little bit, what responsibility does that place on us? Responsibility for taking care of this unique, fragile, interconnected world, and for the generations yet to come who will inherit whatever we leave behind.